and thank you for coming to Space Cadet Training Class. I'm Dan Beeker. I'm advocate for what I call science-based perspective on EMC and PCB design. I call this the billion-dollar mistake, changing the status quo, or a subtitle of how to stop designing products that are likely to fail. So I want to welcome everybody to this session. We're all facing an increasingly difficult challenge using today's components in today's environment. The switches are smaller, they're switching faster, we're getting lower on resistance power switches so that we're switching a high amount of current in shorter and shorter times. At the same time, the EMC standards continue to be extended in both the upper and lower bands. The total amount of radiated emissions you're allowed continues to be reduced. The amount of energy you have to be resistant to continues to increase. And so everything's are going in the wrong direction. And what I'm finding from the customers that I work with and the other signal integrity people that I collaborate with is that the status quo in the industry is to expect to fail EMC between 3 and 5 times. And each time you fail, you have to try to make changes, try to beg for time in the test chamber once you get the new boards built, and hope that it's going to pass. The problem that I'm seeing is that from my customers, when they do make the changes and send the board out for retesting, there's not a high level of confidence. And it's because nobody is understanding the actual root cause of the problem. And unfortunately, it comes directly from a failure to actually understand the nature of the energy that you use. So this is typically not in the schedule. You don't have the time it takes to do these respins in your product development schedule. You typically do not have money in the budget allocated for that. So all of this takes out from new product development and also takes away from the bottom line. This money comes directly from the profit margin, and it affects your company, it affects your customers, and everybody loses because we continue to go down this path of respins and hoping. And that's got to change. That is not engineering. And that's what I'm on a mission to help people to get a better perspective on how the energy behaves, and then apply that perspective to the systems that they design. Is everybody with me so far? Raul?
Yeah, all good then.
Okay. So the problem that I see is that instead of designing your new product, you're busy trying to fix the current one. And what my simple estimate is that multiple billions of dollars are lost each year by good teams designing things they're convinced probably won't work. So when I was trying to understand how we as an industry got to this rat hole that we're in, and continue to accept the fact that we're designing things that are going to fail, I started looking for the thing that I think would be the most influential on this whole bad perspective. And I found a drawing that is the one that I saw during my classes, during my career, and I'm going, this is the problem right here. So I'm sure everybody's familiar with this very simple drawing of how electrical energy works. We got a battery on the left, we've got a switch, and then a load on the other side. And there's typically the arrows are drawn showing what we believe to be the flow of current. This perspective is what is causing good teams to make the wrong choices as they design their systems and printed circuit boards. And the focus from this picture has been on what we call conductors, because it suggests that the energy is flowing in the wires. And that's where things start to fall apart. And as the geometries of the ICs continue to change Gradually, you would go from HMOS and start using HCMOS devices, and it'll be one here and one there, and the frequency of EMC failures gradually increased to where people just became numb to it and almost expecting it. So this is the whole industry has followed this path. And like I said earlier, the design guidelines that we are using were based on what didn't break things when the geometries were large. But when you start to get into smaller geometries, things start to fail. And we, as an industry, didn't seem to notice or care why that was happening. And we just continued along using these badly formulated guidelines and this very, very incorrect perspective of how energy moves. So we've got the battery hooked to a light bulb, and the arrows show what we call current flow. So from this, we started to call the wires conductors. And this is where we start to use the words incorrectly. And my mentor, Ralph Morrison, was very big on language and proper use of the words. So we decided as an industry that these arrows were current flowing. So if the current is flowing in something, then these are the conductors of the energy. So the wire became the conductor because we decided the energy was flowing in the wire. And since it goes in a loop, the idea of a circuit was born because the energy goes in a circle. All these things are incorrect. So the bottom line is, if that was true, when the switch was closed, the energy would be instantly seen at the load, and there would be no such thing as signal integrity or EMC problems. There would also be no such thing as radio because the energy is the same in electrical system or in the air. For some reason, the electronics industry decided when we take electromagnetic field, which everybody believes in, and put it on a printed circuit board, it magically changes to electrons and wires. And looking back at myself, I'm like, how the heck could I believe that from the very beginning? It was, one of those eureka moments when I felt really, really stupid and needed to make the changes. The other thing that's true is there would be no life on Earth because there's no light, no wires connecting us to the sun. So all these things we see around us, the behaviors of radio, energy from the sun, prove to us that it's not electrons and wires, that it's energy in a dielectric or space. But we, as an industry, continue to ignore that fact and apply incorrect philosophies and processes to the designs that we do. So the wires are not the conductors. They form boundary spaces like the banks of a stream. You're creating waveguides, and the energy doesn't flow through the wires. It travels in the space between the wires. The space itself, or the dielectric, is the conductor. That's where the energy is flowing. The energy is carried by the moving electromagnetic fields in the dielectric, not the electrons flowing in the wires. There is movement of electrons. That's displacement current. That is like the wake of the boat. It happens because the field is moving past the matter in the conductors. This perspective is to think about energy as a finite amount of something that's moving in a space, very much like water moving in a pipe. So an ampere is a coulomb of charge moving past a space during a second. It's physically moving in the dielectric, just like water in a hose moving through the system. So Ralph was focused on language. If I would say the wrong word, it would usually end up in a lecture of about an hour explaining to me why that word was wrong and how that word really needed to be reassigned to a proper perspective. And so from these misapplied words, we continue to create a mindset that talks about the flow of energy in wires as opposed to the flow of energy in the dielectric. And like I said in the beginning, when the switches are slow, the geometries are large, it doesn't really matter. So you could do stupid things and the systems would work. But that is no longer the case. In our world, every single switch, every single transistor, every single system needs to be approached with the proper understanding of electromagnetic field physics. So it kind of happened slowly over time. And it's quite like if you put a frog in a boiling pot of water, the frog jumps out instantly. But if you put a frog in a cold pot of water and slowly heat it, the frog will allow itself to be cooked. Well, the electronics industry has allowed itself to be cooked. And now we are soup instead of making things work. So, like I said, it happened gradually because you didn't normally change an entire design from the larger geometry HMOS type devices into the smaller geometry high-speed CMOS. It would be a piece here, a piece there, and sometimes it would cause a failure, sometimes it wouldn't. So this failures per design gradually increased over time, and we just became immune to it, to the point where the status quo is that we expect to fail EMC 3 to 5 times. And this isn't little companies. This is